Hey everyone, let's solve Leetcode problem number 787, cheapest flights within K-stops today. So we were given a graph with n cities and some flights. So for example, here from city 0 we can fly to city 1 and it costs $100. And from city 1 we could not fly back to city 0, so this flight is actually like directional. And we were asked to find out the cheapest price from the starting city to the destination with at most k stops. So if there's no such route, we will return -1. So actually this problem description is quite clear. So in this example, we want to find out the flight from city 0 to city 3 with at most 1 stops. So clearly the answer is this route. It costs $700. And actually there's a route like with cheaper price from city 0 to city 1, then to city 2 to city 3. It costs only $400. However, we have 2 stops here, so this route is not qualified. So let's think about how we can solve this problem. Actually, there are some algorithm to solve it, like the Bellman-Ford algorithm, but today I would like to show you the most intuitive way, which is BFS, breadth first search. So before we start talking about the BFS solution, let's first look at the intuition of this solution. So what if we do like a most brute force algorithm, which is this DFS? So as you can see in the left part of this chart, I already drew such a map with some flights and price marked here. So if we use a DFS, let's say we want to start from the city 1 to city 7. So we will explore the route one by one, right? So we will explore like starting from city 1, we can go to city 2, and we can go to city 7. Then we have nothing here, so we start again from city 2, and we will go to city 4, 6, 7, city 2 to city 3, 4, 6, 7, 3, 5, 6, 7, and also from city 1 to city 3, 5, 6, 7. So as you can see, we need to revisit every route, every city, because like, yeah, we can have a cheaper route but more stops compared with this cheaper, more expensive route with fewer stops. So we have to revisit every city, and the complexity will be exponential. So unfortunately, this brute force solution could not pass the Leetcode time limit. But actually, we can do something better. We can do something called pruning, right? So meaning like we don't need to visit some of those routes below. For example, let's say if we start from this green route first, this route, right? So when we visit this city 2, we can memorize like now we reach this city with 1 stop, and the price was like 200, and then we go further. Now we reached our destination. We can memorize like we reached it with 2 stops and price 700, right? So then we are done with this green route. Now let's look at this orange route. So we are first at here 200, and then we go to this city 4. Here we are 2 stops and 250, right? Then we go to city 6, so it's 3 stops, $300, and city number 7, 4 stops, $450. So then we are done with this orange route. Now we can go to this blue route. So now we were at city 2 and we want to visit city 3. So here it's 2 stops, 300, and here something interesting happened. Now we are at city 4 again. So now we reached it with 3 stops, but $400, right? Here we have 300, here we have 100. So now as we already have a route that reached city 4 with 2 stops and $250, which means like this previous route is more optimal than our new route here, right? Because we have fewer stops but cheaper price. If we can reach a city with fewer stops but cheaper price, why should we go with a route with like more or the same amount of stops but higher cost? This makes no sense, right? So we wouldn't continue with this blue route. So it means like we will never visit this two city again, right? So we are cutting our branches of our decision tree. So this will make our complexity a bit better. So let's finish with this solution. Now, like, we will explore this color, the route with this color. So we are here at city 3, 2 stops, $300, and then we go to city 5, and then we go to city 6. So we reach the city here again. So sorry, I made some typo here. So it's 4 stops, €700, and clearly this is like not as optimal as this one, right? Previously we reached city 6 with only 3 stops but cheaper price. So we wouldn't continue with this route either. So you get the idea of how we can do the pruning and how we can improve our performance. So actually this DFS with pruning solution, it can pass all the Leetcode test case, but I wouldn't show you the code since this video would be too long. And I will attach a link of my DFS solution in the comment below. So now let's look at a better solution, which is a BFS solution. So normally, like when we talk about like a shortest path, whatever, BFS would be our first choice, yeah? So now you will see the difference between DFS and BFS. As you might know, for DFS, we are exploring like route by route in this order, but in the BFS, we are exploring our graph like layer by layer, right? So we start from city number 1, and we will first explore these two cities, 2 and 3. So they are like one stop, $200, and one stop here like 400, right? We have this route, but now we are only exploring the cities with one stop only. Then we are done with the first layer, and now we will increment our stop. So now we will explore a city where we can reach by 2 stops, yeah? So now we can reach city number 2, like 2 stops, 300, and city number 4, this is 2 stop, 250, right? So then we can also reach city number 7 with 2 stops, that is 2 stops, how much is it? Sorry, 800, yeah, it doesn't matter. So now let's, we are done with the 2 stops, we will increment our stop again, and we will do the city with 3 stops, yeah? And I wouldn't continue with this like simulation, but you will get the idea. So now we can notice one thing, because we will reach a city for the first time always with the fewest amount of stop, right? For example, here for city number 3, we will first reach it from here with only 1 stop, which costs 400. Then for the second time or the third time, whatever time we reach it again, we are coming with more stops, right? So in this situation, we have to have a cheaper price in order to revisit this city. If, like, for example, if we could revisit, let's say if this is 400, then it means like we could reach city number 3 from city number 2 with how much? With not 400 but 600. Sorry, I made a mistake here. $600, right? So now this 600 is more expensive than the previous route, which is 400, and we are coming with 1 more stop. So it doesn't make sense to continue with this route, right? So this is like our idea. Unlike the DFS, we are exploring the graph by depth first, and we don't know like we will reach one city by how many stops. Here we will always reach a city with fewer stops first, and then if we can revisit it again, we will reach it with like more stops. So here we have to have a cheaper price in order to continue with our graph traversal, yeah? So this is basically our idea, and now I will show you the code. Since this video is quite long, like I already typed the code, but I will briefly explain it line by line. So first, we will use a hash map to just store our flight information. So basically I will use the city number as the key here, and then I will use the pair of what did I use? I used pair of the destination city and the cost as the value of this hash map, and I will call it like networks. It doesn't matter. Then I will first initialize our final result as a very big number. You can use int max if you like, but it doesn't really matter. And then we will have a vector to store the minimum price for the routes we have already found for certain city, right? Because we want to always remember what is the previous minimum price to reach this city with fewer stops. So with this intuition, first we can convert our flight, this is a 2D vector, into our hash map, which is pretty simple. I will skip this part. It's just like we will iterate through this flight and then put it into our hash map. Yeah? And then we will initialize our minimum price vector. So we will initialize the price to reach each city as a like very big number or int max. It doesn't matter. And then we will start our algorithm. So first we will mark the cost for the source city, the starting city, as 0, because we didn't need anything to start from here, right? Then for the classical BFS, we need a queue. So I will put the city, stop, and price into our queue. I will use a tuple here, but you can also use like a vector. It doesn't really matter. Using tuple just make it a bit cleaner. So then first I will make a tuple for our starting city. So it's like the source city, 0 stop and 0 cost, yeah. And then I will put it into our queue. So I will also initialize the stop as 0. Then we can start our BFS traversal. So here first, of course, as a normal BFS, we will make sure like we will continue if our queue is not empty. And here I added another condition which is like our stop must be less or equal to our limit k here, right? Because we want to find the route maximum with at most k stops. If we exceed this limit, we will break the loop and it's done. So first we want to do it like layer by layer. So first we will get the size of our current queue, and then we will process those elements, right? So if the size is greater than 0, we will continue. Of course, here we have to decrement the size after each loop, and then we will get our current city, current stop, and current price. So those price are like cumulated price, right? So the current city is just the like the city we want to process, which is the front of our queue. And then we can first quickly check if our current price is already greater than our optimal price we have already found to reach the destination. We don't need to continue with this loop, right? So we can directly pop our front queue front, and then we will decrement the size and we will not continue this cycle. So then if the condition is not satisfied, which means like our current price is still less than our result we have found, we will now we will explore the possible destination from the current city, which means starting at, for example, this city 1, we will explore city number 2 and 3. So we will get our next city, the cost to fly to next city, and then our new cost would be our current price plus our next cost, right? So here we will do our check. If the new cost is less than the minimum price we have already found to reach the next city, which means like it's worthwhile to continue this route. So we will update the minimum price for the next city, and then we will put it into the queue. And here we will also check if our next city is our destination. We will update our result, right? So after all those procedure, we will pop the front of the queue and we will decrement the size. And of course, when the size reaches 0, it means we have been done with one layer, so we will increment our stop. So yeah, so as you can see here, if our the new cost is greater than the current minimum cost to reach next city, we wouldn't push any element to the queue, right? So this element will be popped and our root would not increase. So that's where we can like reduce our complexity and improve our performance. So finally, we just need to be careful. Like if we didn't find any root, which means our result is still the int max, we will return -1. Yeah? Otherwise, we will return result. So now if we submit this code, as you can see, like it beats around 80% of the C++ program, which means this is like a quite efficient algorithm. So I think if it's the first time you see this problem, and if you couldn't think of something like Bellman-Ford, this breadth first search would be really like a intuitive and relatively easy to be implemented algorithm. So I hope this video could help you to understand this problem, and if you like my video, please follow my channel. Thank you.